All right, let's work through a couple more difficult examples. So here's a pop instruction. So this instruction is certainly more complex than the one that we just looked at. So it's actually doing something during all 6 stages of the CPU. And you can see that, that it's doing a pop from the stack. So this is going to be touching memory and potentially modifying a register. So we are going to be, so I've given you an initial value of a register and an initial value of a location in memory. All right, so as always, pause the video, see if you can work this out by yourself, and then we'll work through the answers together. Okay, so the fetch stage is always fairly straightforward, and in fact, this is project 3, just reading in all this information and getting it into a struct appropriately. So we're always just going to be reading in the first byte of the instruction and separating it into the I-code and the function, the ifun. So here that's B and 0 respectively. We have a register here, so we're going to read the register byte and separate it into RA and RB. You'll notice that one of those we're not using, so we're only using the RA in this case. And then we'll calculate the address of the next instruction, which is the val p. All right, so then we move to the decode phase where we are reading a register. And you'll notice that we read the value of RSP twice. And we're saving it into 2 different places. So we've got it coming out as val A and val B. You may be wondering why we need to read it twice, why we need to have 2 copies of it. But hopefully that makes a little more sense as we go along. So the next thing we do is we go to the execute phase where we're doing an arithmetic operation using our ALU. Here's an example of where we're doing an arithmetic operation not because we're doing an arithmetic instruction, but because we need to calculate a new effective address. So we need to calculate the new stack pointer since we're popping something off the stack. Since we are popping off the stack, we need to add an offset to the old stack pointer. So we're taking one of our copies of the stack pointer, so val b, we're adding 8 to it, and we're saving that as our effective address, or val e. All right, so next we need to actually read from memory. So we need to pop the value off of memory. And so here we're going to use that other copy of A. And so now maybe you see why we have 2 copies so that we can potentially be doing some of this at the same time. But in any case, we're going to take the other copy of the stack pointer. We're going to read 8 bytes from memory at that location. And we're going to store that value as val m, so the value from memory. Moving into the write back phase, we actually have, and you can see the concrete values over here. I'm sort of talking through what's happening, but the actual numbers are over here. And then when we get to the write back phase, we actually have 2 registers that we're writing. So you remember that our register file supported up to 2 writes. So we're writing the new value of the stack pointer, which is going to be our newly calculated address coming from the ALU. So that's 128. And then the actual register, the value that we popped off the stack is going to go into RA, which in this case is RAX, which we determined up here when we did the fetch. And that's going to be the value 9, which I told you ahead of time. And that value is coming from the memory read. And then finally we get to the PC update where we've sort of already done the register changes that were important. And so now we're just going to update the program counter to move on to the next instruction. So we would say then that the semantics of this instruction are that it sets RAX to 9, it sets RSP to 128, and it increments the program counter by 2. All right, so here's another example. So again, I would strongly suggest that you pause the video and work through it yourself, and then come and check your answers. Okay, so this one's actually potentially not quite as complicated as the one we just did. So again, we're reading the first byte in and splitting it apart. We are going to be reading an immediate value from the instruction. Since this is a call, we know that this is the destination address. So we would hope to see this value used as part of the PC update at the end. And if we kind of skip ahead a little bit, we'll see that that is exactly what happens. So this is going to be the address of the instruction that we want to execute next. Val P is the address following this call instruction, which you may remember is the value that we want to push onto the stack. So that's what the rest of this needs to do. So we've already seen the part that transfers control. So we read in the address of the call of the procedure that we're calling, and that's going to be what we set the PC to at the end. But we want to take this address of the next instruction and push that onto the stack so that when we execute a ret instruction, that address is there so that we can jump back to it. Okay, so in order to do that, we need to figure out where the top of the stack is right now. So that's what we do during the decode phase. We grab the stack pointer and we save it. So here the stack pointer is 100 and yeah, so sorry, the value of the stack pointer is 128. So that's the address where the stack, top of the stack currently is. We need to calculate a new value for the top of the stack. So we'll go ahead and take that and calculate val E as val B minus 8. So we want to, we're going to be pushing something onto the stack. So we need to subtract an offset to get the new top of the stack. We're going to go ahead and save that return address. So that's the val P that we calculated up here. So that's what gets saved to memory at our new effective address. So that's the new slot on the stack that we created by subtracting 8 from the old stack pointer. And then during the write back phase, we are going to update the stack pointer with our new stack pointer value that we calculated during the execute phase. Okay, so those were two significantly more complicated instructions, and I wanted to include those so you had some examples of more complicated things. If you need to watch this a couple of times just to catch all the nuances going on there, that's totally fine. But hopefully you'll come into the lab prepared to do a bunch of these. So we're going to ask you to trace through a program and give us the semantics for a whole program execution as it runs on a y86 CPU. So again, if we were to summarize the semantics here, we would say that this instruction sets RSP to 120, stores the return address 014 at the old value, and sets the PC to 041. So this is a fairly complicated instruction. It's doing a lot of things. All right. So I just wanted to wrap up this video with putting up the overall y86 semantics. So there are 12 instructions here. There's another instruction called IOTrap that we aren't giving you the semantics to because it's a little bit of an outlier, but these are the main instructions for y86.